The universe is a vast and wondrous place full of mystery. Humans have gazed up at the cosmos and wondered about its secrets since the dawn of civilization. Even with our modern scientific knowledge, there are still many unanswered questions about the origin and nature of the universe. This article will explore some of the biggest mysteries that continue to puzzle astronomers and physicists. The origin of the universe. Perhaps the greatest mystery is how the universe began. The dominant theory is that the universe started with a massive explosion called the Big Bang about 13.8 billion years ago. All of the matter and energy in the cosmos emerged from a single infinitely dense point. But what happened before the Big Bang? What triggered this massive expansion of space and time? We currently have no way to see or receive information from before the Big Bang, so determining what came before it remains elusive. The accelerating expansion of the universe. The accelerating expansion of the universe. In the 1990s, astronomers discovered that not only is the universe expanding from the Big Bang, but this expansion is accelerating. Some unknown force, dubbed dark energy, appears to be pushing galaxies farther and farther apart at an ever-increasing rate. The nature of dark energy remains a perplexing riddle. It does not appear to interact with ordinary matter through any of the fundamental forces other than gravity. More precise measurements of the acceleration may help shed light on this mysterious substance that comprises 68% of the universe. In the 1990s, astronomers discovered that not only is the universe expanding from the Big Bang, but this expansion is accelerating. Some unknown force, dubbed dark energy, appears to be pushing galaxies farther and farther apart at an ever-increasing rate. The nature of dark energy remains a perplexing riddle. It does not appear to interact with ordinary matter through any of the fundamental forces other than gravity. More precise measurements of the acceleration may help shed light on this mysterious substance that comprises 68% of the universe. Dark matter. Along with dark energy, dark matter is one of the greatest mysteries in cosmology today. It is thought to make up about 27% of the universe. We cannot directly observe dark matter, but we know it must exist because of its gravitational effects on visible matter and light. Dark matter appears to exert gravitational force, but does not interact with light or normal matter. Determining what exactly dark matter is remains an open scientific question. Leading theories propose it is composed of undiscovered subatomic particles that interact very weakly with ordinary matter. Black holes. Black holes are regions of extreme gravity, caused by stars collapsing in on themselves after supernova explosions. Their gravity is so strong that nothing can escape, not even light. Black holes warp space-time and cause massive celestial bodies and clouds of gas to orbit around them. Their existence was theoretical for many years until astronomers finally detected them through their gravitational interactions. However, the interiors of black holes remain a mystery. Exactly what happens when matter and energy fall into a black hole is unknown. Resolution of the black hole information paradox remains one of the crucial problems in physics today. The universe is missing matter. Surprisingly, all the normal matter that we can observe, stars, galaxies, planets, gas, dust, etc., only makes up about 5% of the total matter content of the universe. So where is the remaining 68% of the universe's matter? This is one of the significant outstanding problems in cosmology. Some possibilities are that dark matter makes up some of the missing matter. Another potential source is high-energy particles called neutrinos that rarely interact with normal matter. However, these and other explanations do not seem to completely account for the surprisingly low amount of visible matter we can currently detect. The nature of gravity. Gravity is the weakest yet most puzzling of the four fundamental forces in nature. We do not yet have a theory that definitively explains gravity, like we do for electromagnetic and nuclear forces. Einstein's theory of general relativity describes gravity not as a force, but as a consequence of the warping of space-time by massive objects. But general relativity remains incompatible with quantum mechanics. Finding a quantum theory of gravity is one of the holy grails of modern physics. Such a theory could finally make sense of the force that governs the motions of the cosmos. Cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe appears to have undergone a period of exceedingly rapid exponential expansion called cosmic inflation. This sudden ballooning smoothed out large-scale irregularities and distributed matter evenly, explaining why the cosmos today looks mostly the same in all directions. Cosmic inflation helps resolve some problems with the standard Big Bang theory. However, the physics that drove this growth spurt in the infant universe remains poorly understood. A fuller theory of the initial moments of the universe must explain what triggered cosmic inflation. The multiverse idea. Some cosmological theories have suggested the possibility of a multiverse containing an infinite number of universes. This arises from the concept that our universe may be only one of many. For example, cosmic inflation could be eternal, constantly spawning new universes. Each universe might have different laws of physics and fundamental constants. However, there is currently no observational evidence that universes other than our own exist. The multiverse concept remains controversial and contentious among scientists. Further research and new physics may be needed to either prove or disprove the existence of additional cosmic realms beyond our own. Cosmic microwave background. Some of the deepest mysteries concern the cosmic microwave background (CMB) radiation. The CMB is faint electromagnetic radiation that permeates the universe, thought to be left over from the Big Bang. By studying slight temperature differences within the CMB, cosmologists have gleaned tremendous knowledge about the origin, shape, and evolution of the universe. However, anomalies in the CMB remain unexplained. For example, it appears mostly uniform, but contains unusual large-scale patterns of hot and cold spots. These oddities in the primal radiation could suggest unknown features or processes in the early universe. Further investigation of the CMB may unlock new physics from the time when the cosmos began. Dark energy's nature and role in cosmic evolution. Perhaps no mystery has baffled cosmologists more in recent decades than the nature of dark energy and its role in the universe's evolution. As previously mentioned, dark energy seems to explain the accelerating expansion of space, but little else is known about this invisible force. Unanswered questions include whether dark energy has varied over time or remains constant. There are also competing theories about whether dark energy arises from immutable laws of physics or is an intrinsic property of the vacuum of space itself. Upcoming astrophysical experiments will shed more light on dark energy's role in cosmic inflation, the distribution of matter, and the ultimate fate of the universe. Plumbing the mysteries of dark energy remains essential to creating a complete model of the past and future evolution of the cosmos. Origin, distribution, and composition of ultra-high energy cosmic rays. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that zip through space at nearly the speed of light. Ultra-high energy cosmic rays, UHECRs, are the rarest and most energetic of these particles, packing huge amounts of energy. But the origins and makeup of UHECRs remain unknown. They rarely interact with matter, making them hard to study. Scientists have proposed exotic sources like supermassive black holes, but no consensus exists on exactly what objects can accelerate particles to such tremendous speeds and energies. Upcoming probes like NASA's probe of extreme multi-messenger astrophysics, POEMA, will examine UHECR distribution and behavior for clues about their origins, mechanisms, and composition. Understanding these ghostly particles could unveil previously unseen processes at work in the most extreme environments in the universe. The formation and evolution of the first stars and galaxies. How did the very first stars and galaxies form? This remains one of the most significant unsolved riddles in astronomy. The standard theories of star and galaxy formation do not seem to work for the earliest celestial objects created after the Big Bang. The primordial universe contained only hydrogen, helium, and a little lithium. Heavier elements did not yet exist. So what dynamics allowed the first stars to coalesce in this nearly empty environment? How did these pioneer stars then ionize the intergalactic medium and forge the first heavy atoms? Current models cannot fully explain these foundational events. Next-generation telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope could reveal new insights into the emergence of the earliest light sources and beginnings of cosmic structure. The fundamental nature of time. Is time truly a fundamental concept, or could it be an illusion arising from even deeper physics? Some theories in quantum mechanics and quantum gravity hint that time may not be a basic ingredient of reality. The flow of time emerges from phenomena like entanglement and entropy that occur at microscopic scales. Some physicists propose time is an approximation that emerges from more basic timeless laws governing the universe. Untangling time's nature could require a quantum theory of gravity, which continues to elude physicists. Understanding whether time is fundamental or arises from deeper physics remains an enigma at the forefront of modern science. Possible existence and influence of extra dimensions. Are there hidden dimensions beyond the three-dimensional space and one-dimensional time that we can perceive? Some theories, like string theory, require extra dimensions to work mathematically. However, current experiments have found no conclusive evidence of dimensions beyond our normal spacetime. If they exist, these extra dimensions must be curled up or otherwise invisible to modern physics. However, they could have had profound influences in the early universe. Extra dimensions may help explain cosmic inflation or the extreme weakness of gravity relative to other forces. New methods of probing minuscule distance scales or high-energy environments may reveal whether extra dimensions really do exist and better explain their potential roles in the evolution and structure of the cosmos. The possibility of warped spacetime and traversable wormholes. Einstein's general relativity describes gravity as warps and curves in the fabric of spacetime. This suggests the possibility of extreme distortions like wormholes that act as tunnels connecting distant regions or even different universes. While theoretically valid solutions to the equations of general relativity, traversable wormholes remain hypothetical. But some scientists propose that advanced civilizations might be able to engineer or take advantage of naturally occurring wormholes for faster-than-light travel. Wormholes may also offer a window into the quantum foams hypothesized to exist at unimaginably tiny scales. Unfortunately, it remains uncertain if spacetime could become warped enough to open traversable passages without collapsing. Proving the realistic possibility of wormholes may require new physics beyond our current theories. The search for unification of physics. Many physicists believe all the fundamental forces and particles are manifestations of a single unified field. Finding a theory of everything that combines all physical laws has proven immensely difficult. Unifying quantum mechanics and general relativity remains one of the most formidable challenges in theoretical physics. Some speculate that a quantum theory of gravity will require radical new concepts like supersymmetry or higher dimensions. Other proposed theories incorporate exotic ideas like strings, loops, emergent spacetime, holographic duality, and varying fundamental constants. Which approach, if any, may lead to the coveted unified physical theory remains unknown. Successfully describing all known forces and matter using one coherent theoretical framework would revolutionize our understanding of the cosmos. These and many other deep mysteries continue to intrigue scientists and fuel cosmic research. Future observatories, particle colliders, and theoretical advances will undoubtedly reveal new clues to these enigmas that define the frontiers of astronomy and physics. We have learned much, but it is clear the universe still holds far more secrets left to uncover. Confronting these cosmic puzzles inspires us to expand the boundaries of human knowledge about the origin, evolution, and fate of the universe. As long as mysteries remain, our quest for understanding will continue, leading us ever deeper into the foundations of creation. Don't forget to like and subscribe to our channel so you don't miss new videos.